everyone, and welcome to another unit. This one is about equilibrium, looking at a state of balance. And this lecture, we're going to be focusing on chemical equilibrium and equilibrium constants. And when we're looking at these equilibrium constants, we're going to look at concentration constants and constants when we are looking at pressure units. So most reactions are reversible. And if we think about this reaction, if we have reactant A and reactant B that are colliding with one another, and they will, before we even look at products, these two reactants are colliding with one another, so they will produce a product because of their collision. So initially, only A and B exist. So only the forward reaction is possible. But as C and D build up, the reverse reaction speeds up while the forward reaction slows down, because if you think, we're having less and less reactants and more products are being formed. But then these products are also hitting against each other. So that reverse reaction can then start to happen. And eventually, the rates will be equal. Not the concentration per se, but the rates will be equal. Let's look at this graph here. We're looking at reaction rates, and then this is as time goes on. Our forward reaction, let's say that we had the reaction A plus B creates product C plus D. And we can see here that initially we have a very high reaction rate. And this is our initial, our A plus B. And we can see it's really high as our forward reaction progresses. But then we can also see down here is our low reaction rate, that the reverse reaction starts to pick up as time goes on until it has reached here, this dynamic equilibrium. And that is telling us that that is when A plus B that is created, C plus D, is happening at the same rate as C and D combining together to create A plus B. And this right here is the way of showing that this forward reaction and the reverse reaction rate is in dynamic equilibrium. So what's equal at equilibrium? The rates are equal. Okay, the concentrations are not, and the rates are determined by concentrations and activation energy. So if we think about, and we've talked about this in this last thermodynamics unit, we can have a reaction with a very large activation energy. Remember, that's this energy right here required for this reaction to happen, as compared to a very small activation energy. So this one is obviously going to have a much smaller or quicker rate because it has a lower activation energy. So rates are determined by concentrations and activation energy, but that net concentration does not change at equilibrium. And if we look back at that last graph that we did, we can see here that the rate that this forward reaction happened, A plus B, happened a lot quicker than our reverse reaction. But once we hit this dynamic equilibrium, then that reaction rate is staying the same. That is when going forward and backward, that rate is equal. So let's look at the concept of equilibrium. An equilibrium mixture exists for the decomposition of N2O4. So we have dinitrogen tetraoxide. And it is in the gaseous stage. And it is decomposing into 2 units or 2 moles of nitrogen dioxide, also in the gaseous phase. And it is in dynamic equilibrium. So we can see that the forward reaction is happening at the same rate as the reverse reaction. So remembering kinetics, and kinetics is the rate at which reactants are disappearing. So we have here our reactants that are disappearing to create these products. We also have the reverse happening. So I'm just going to write down here, this is the rate and when we think about the rate at which the reactants disappear, we're looking at that change in the concentration of the reactants over time, right? And this is experimentally determined. I mean, there are scientists that are sitting there with a stopwatch to see how much time for my reactants to disappear and to create the products. So we're assuming that these are both elementary reactions. Now also notice that this dynamic equilibrium, if you notice, there might be a time in the notes where my keyboard did not do a good job or it wasn't able to make this, so you'll see a double arrow. This is not correct. This shows resonance, not dynamic equilibrium. Dynamic equilibrium has a forward arrow and a reverse arrow. This is the correct way to show dynamic equilibrium. Okay, so to write this, we need to determine what this rate is. So we're going to write this rate. We are going to use Kf, the constant for the forward reaction. So what we're measuring is how long does it take for our reactants to disappear. That's what our rate log constant in the forward direction is going to tell us. The rate, the rate that it takes for our reactants to completely disappear to create those products. So since we're looking at the rate of disappearance of our reactants, we're going to write, all right, so the rate of disappearing, the concentration of N2O4. So we can also say that the rate in the reverse reaction is equal to the rate log constant, and we're going to denote that in the reverse direction. And I'll do this, reverse direction of the concentration of going in the reverse way of, oh, and this is not balanced. I forgot the 2 right here. Sorry, we're going back. Of NO2, but we need to note that, notice that this NO2 has a stoichiometric, right? We have 2 moles here versus 1 mole here. So we need to square this. And when we're looking at concentrations and rate laws and kinetics, whenever we have ratios here, these numbers are going to be our powers. They are very important when it comes to stoichiometry when we are doing kinetics and equilibrium. These coefficients become the power with which we raise our concentration values. So looking back at this one, since we have 1 mole of this is just raised to the 1. You can either put it or you can leave it off. Now, again, just as a reminder, when we have these brackets indicate molarity, which denotes moles per liter. And remember, we're also looking at these 2 rates. When they're in dynamic equilibrium, the rate of the forward disappearance of our reactants is also equal to the rate of the reverse reaction when NO2 concentration is diminishing and turning back into N2O4. So in one way, these are my reactants. In the opposite way, this is the reactant, which is why we're able to say the rate for the forward reaction, the rate for the reverse direction, and it's when they are equal to each other. We can then take this and we can say, since these are happening at the same rate, they are equal to one another. So then we can write this expression and we can say, well, Kf times N2O4 to the raised to the power of 1 is equal to the reverse direction rate. So Kr, the constant in the reverse, times NO2 to the raised to the second power. And again, that's because of our balanced chemical equation that it takes 2 moles of that, so it's raised to the power of 2. And this is when they are in equilibrium. So I'd like to manipulate this equation here and get Kf over Kr, get my constants all together. And so to do that, I'm going to divide, so I can have Kf all by itself. I'm going to divide by N2O4. That'll get rid of that. And then I'm going to divide both sides by Kr to get rid of Kr on the right. And that leaves me with a concentration of NO2 squared over N2O4. This ratio here is defined as our equilibrium constant. This equilibrium constant, the magnitude of this number, is very important when looking at rate laws, and especially to the chemist. So essentially what we did to find the equilibrium rate law, we looked at the forward reaction when we have dinitrogen tetroxide. Forward reaction creating 2 moles of NO2. So that rate for the forward reaction, Kf, was equal to that concentration of N2O4. So we are getting rid of N2O4 in the forward direction. In the reverse direction, we took that rate law, Kr, the constant in the reverse direction, of getting rid of 2 NO2s. Again, it's getting rid of the reactants. And in the reverse, the NO2 is our reactants. And notice that we raised it to the power of 2 because of the stoichiometric ratio. It is stoichiometric dependent. So then we arranged that, so at dynamic equilibrium, when both of these are happening at the same rate, then they are set to be equal to one another. We rearranged this so that we had the forward reaction rate and the reverse reaction rate. And when we did that and divided both sides, so we have Kf over Kr, which was equal to NO2 to the power of 2 over N2O4. We have the reactants, we have our products over our reactants. All right, so by doing this, we have our equilibrium constant. And this number right here is our equilibrium constant, which will often be denoted as Kc, our equilibrium constant, when looking at concentration. Or by Kp if we're looking at the equilibrium constant when looking at pressure. And again, concentration, dealing with molarity. So Kf over Kr is then denoted as our equilibrium constant. Kc, or like I said, we will also be looking at Kp, and pressure we often will look at in atmospheres, kilopascals, any other pressure units. So a long-winded answer to tell us what is equilibrium? Well, it's a dynamic state when the reactants are turning into the products at the same rate that the products are turning back into the reactants under the same conditions. So then, again, we rearranged. We have our product over our reactant, again, with our stoichiometric ratios. Gave us our Kf over Kr, which is our constant, and that constant is called equilibrium constant. Once that equilibrium is reached, the concentrations of our products and our reactants no longer change. There is no net change. The reaction still occurs. A and B are still reacting to form C and D, and C and D are still reacting to form A and B. The reaction still occurs, but it's in a state of dynamic equilibrium. No more changing in the concentrations. The opposite of dynamic equilibrium is static, and this is the opposite, which means no movement, but this still has movement. Reaction is still occurring back and forth. We're just not changing the concentrations. So for any reaction, we can use this law of mass action. For any reaction happening, we can write the equilibrium constant expression. This is just the generic. The little a stands for our coefficients, which is, remember, when we balance chemical equations, the numbers in front of our chemical species. And then this is our actual chemical compound, or whatever species we're actually having for reactants and products. So for any chemical compound, we have the equilibrium constant expression, Kc. And essentially, it's always going to be our products over our concentration of our products over reactants. And again, this Kc, C is concentration. Concentration is denoted by brackets, which shows us molarity. We might also, like I said a few times now, we also can look at Kp, which is the equilibrium constant for pressure. And again, that's will be denoted using atmospheres, most likely. But this is just a showing us that we would take our products, our concentration of C raised to, if there is any power, any coefficient to C, times D to the power of little d. So this is our products. And again, A and B are our reactants. And we can see that we have capital A and B. Those are our chemical species, and raised to the power of, if they have any kind of coefficient. So that equilibrium constant that gives us our numerical value, again, we obtain it when we substitute equilibrium concentrations into that expression. The subscript indicates that concentrations expressed in molarity are used to evaluate the constant. And again, that concentration is because we denoted this Kc. That's our concentration. And I said, even in this chapter, we're going to be looking at Kp, pressure constants. And in the next few chapters, we're going to be looking at a lot of other constants. When it comes to, we'll see Ka, which is looking at the constant dealing with acids, and Kb's dealing with bases. We'll see Kw, looking at the constant with water. We'll see Ksp, constant dealing with solubility and salts. We'll see Kf, dealing with ions. And what's great about all of these constants is that we will find them all in the same way. So that constant that we will be finding is a numerical value. It does not have any units. It is a number, and we will look at that to see the magnitude of that rate of reaction. So again, it's stoichiometry dependent. The equilibrium constant expression depends only on the stoichiometry of the reaction, not on its mechanism. We really need to have that balanced equation so that we can use when we're looking at concentrations, if there was a 2 in front of it, then it's going to be raised to the second power or to the third power. So we have to know those stoichiometry ratios. The Kc, the equilibrium constant at any given temperature, does not depend on the initial amount of reactants and products. Again, we don't care the amount of it. What we're looking at is the rate of the reactants becoming the products and the products coming back to the reactants. We're looking at this aspect right here where it will be equal, the rates will be equal, and the value of Kc depends only on particular reaction and on the temperature. Temperature makes a big difference because obviously if the temperature was raised, then that reaction rate would be different because those particles are moving faster. So most of the, and this would all be documented, right? But most of the time the reactions are being done at room temperature. But if they're being done different, it would be something that would be done in the lab and would be highly monitored. So we do not care what that initial amount is because again, we could be starting with different amounts. What we care about is when they are at this point in dynamic equilibrium. Let's practice writing some equilibrium expressions. So let's say that I have this reaction. Again, this would be one where that darn computer, where I would need to write my dynamic equilibrium arrows correctly. So here's my reactants, here are my products. So to write my Kc, my equilibrium expression for the concentration of these rates, my rate reaction, I need to use, let's see, we're going to just rewrite. We have 2 O3s, which is ozone, decomposing into 3 molecules of molecular oxygen, both in the gaseous stage. Good, and I rewrote the equation correctly this time. So here we're going to write our products. So I have O2 and I have 3 O2s, so it's going to be to the third power, over my products over my reactants. I have O3 raised to the second power. And again, this C is telling me, these brackets are telling me it's my molarity, which is moles per liter, telling me that we're looking at the equilibrium expression constant for the concentrations throughout this chemical reaction. All right, let's look at the Kc for number 2. So again, here's my, oh goodness. So here's my products. I have NaCl. So I'm going to do a concentration of NaCl raised to the power of 2 over, so my products over my reactants. In my reactants, I've got NO, so the concentration of NO to the second power, and Cl2, and that's just to the power of 1. So again, looking at K, the equilibrium constants are related not only to the kinetics of the reaction, but also to its thermodynamic measurements. It's actually measured in measured in activities, not concentration or pressure. We're not going to be dealing with it in this course, but so that's beyond what we're going to be studying. So it is accepted to not include units on equilibrium constants. So K is constant at any different temperature, but temperature does affect the rate. If we increase the temperature, then the K would change. So it is important that we know the temperature that the reaction is happening at. And the equilibrium concentrations don't have to be the same, only K. Equilibrium is a set of concentrations. So there's unlimited. We could change the concentration, we could change the volume, we could change so many other things, aspects about the reaction. And K will hold true, but it needs to be at the same temperature. If we change the temperature, then the reaction constant would change. So that is something, again, that we need, that would be verified in the lab, but temperature does affect rate. We know it can speed it up, it can slow it down. Let's put this to the test. So here we have some experimental data for this reaction that we were just looking at. N2O4 creating 2NO2, and same with back. So here we have experiment number 1. We initially had no N2O4, but we initially did have 0.02 molar. We know that these brackets tell us its concentration, so that's 0.02 molars of NO2. So since we did not have any N2O4, 0 of our reactant here, we know that this reaction is solely going in the reverse reaction initially. But then we see that it does reach equilibrium here. And at equilibrium, we can see the concentration of N2O4. So we went from 0 to 0.0014 molar concentration. And at equilibrium, my NO2 was consumed because I started at 0.02. I now have 0.0172 concentration. So remember, our Kc we know is products over reactants, and we just did this on last slide, a couple slides ago. NO2 to the second power, right? Products to the power of 2 over reactants, which is a concentration of N2O4. So let's put this to the test and see at equilibrium, what is that constant? So for number 1, notice I initially started with 0.02 molar. So we're going to do our products, our NO2, so we're going to do Kc is equal to 0.0172 squared over concentration of N2O4, which is 0.0014. Let's calculate what our equilibrium constant is. So I'm going to, hopefully you can see this, 0.0172. I'm going to square that. I'm going to divide it by 0.0014. And I get 0.211. Again, it's just a number, no units. Now let's look at experiment number 2. Experiment number 2, we initially started with the same 0, but my concentration changed. I went from 0.02 to 0.03, so I have a higher concentration of NO2. And at equilibrium, we can see that not the same concentrations here. My N2O4 increased. And I also consumed my NO2 in equilibrium, so it went from 0.03 to 0.0243. Okay, let's use that same equilibrium constant and do our products, which is our NO2. So we're going to take 0.0243, square it over our equilibrium concentration of N2O4, 0.00280. Let's plug this in. So we're going to do 0.0243 squared, and we're going to divide it by 0.00280. Notice we got 0.21, and that 8 would round that to a 1, so 0.211. Let's look at experiment number 3. Again, we can see that, so I'm increasing the concentration. We went 0.02, 0.03, 0.04. Again, notice that my equilibrium is different concentrations for both of these. Well, let's still find it. Kc for this guy, I'm going to do, I always have to look. I'm like, which one? Okay, NO2 which is this guy, 0.0310 squared over equilibrium is 0.00452. So I'm going to do 0.0310 square it, divided by 0.00452. 0.212. Okay, really close, within 1,000. Let's check on this last one. Now on this last one, notice that I now have an initial concentration and I don't have any NO2. So in this case, we're going in the reverse reaction, right? Because I only have reactants. I don't have any products initially. So here's a case of going in the opposite direction. So we can see that the N2O4 is being consumed. Notice I started at 0.2 molar and I'm finishing at 0.004. And this NO2 is gaining concentration because I started with 0 and now it's at 0.03. So let's do the same KC here. And again, I'm going to do my concentration of 0.0310 to the second power over 0.00452. And I guess I don't need brackets here when I have my numbers. These can just be parentheses. Just used to writing the brackets by writing the expressions. So 0.0310 squared. And I'm going to divide it by 0.00452. Notice I get 0.213. Notice that this equilibrium constants are staying consistent throughout all of these trials. So the moral of the story is, no matter what the concentration is initially, or even at equilibrium here, when we have this reaction and we set up to find our concentration constant at equilibrium, no matter what we change here, we have a constant number for our equilibrium constant, looking at the rate of reaction. So like I said earlier, we can look at equilibrium constants in terms of pressure. When the reactants and products are all gases, we can write the equilibrium constant expression in terms of partial pressures instead of molar concentrations. So if we have the same setup where we have A plus B yields C plus D, we can write this, and these are all gas in the gas phase. There we go. We can write this in terms of Kp, and before we used brackets by looking at the concentration of A to the power of, products over reactants. So we would look at the concentration of C to the power of C. Well, here we're just going to write the partial pressure of C raised to the power of C times the partial pressure of D to the power of D. So that's my products over reactants. And then again, we would look at the partial pressure of A to the power of A times the partial pressure of B to the power of B. And so our P is representative of partial pressure, as opposed to brackets, which is concentration, which is in the form of molarity. So looking at Kp and Kc. So for any reaction, the numerical value of Kc is usually different from Kp, simply because looking at Kp, remember we said it's for gases only. So for finding Kp, if there's anything in that chemical equation that was solids or liquids, they drop out. So that's why Kp would be different than Kc. Kc would include the concentrations of, if there was liquids, say, then that would not be included in Kp. So it is important to indicate whether we're looking at concentration or pressure, which one of those equilibrium constants you're using. We can convert from one to the other. We're going to look at that at the next slide. So we're going to look at some equations here. Do you remember looking at gas laws? And we have this ideal gas law where we compared pressure and volume. So PV equals nRT. So where P stood for pressure, V for volume, N stood for the number of moles. R was our gas law's constant, and T was temperature in Kelvin. So this pressure, again, could be in atmospheres, it could be in kilopascals. Okay, we've got volume, usually in liters. Our N is our moles, and this R was one of two things. Depending on what our other units were in, R could be 0.0821, and that would be in liters, atmospheres over Kelvin mole, or let's see, or R could equal 8.31, but that units would be liters, kilopascals over Kelvin mole. So we've got all these different units here, but think that molarity, when we're looking at concentration, so think of Kc when we would find the concentration constant, that dealt with molarity. Remember our brackets. And molarity is equal to moles per liter. Notice in this equation, we do have moles and we do have volumes in liters. So essentially, that's equal to looking at this equation and doing N over V, which if you look over here, pressure is equal to N over V. So we can take that concentration constant, Kc, which is our N over V, our moles per liter, concentration is N over V, and we can plug it into our equation. All we did here was divide both sides by volume, so we could have N over V times RT. All right, now, again, why are we doing this? Well, because if I'm converting between concentration constant and the pressure constant, because Kc is for aqueous solutions and for gases we could use, but Kp for pressure is gases only. So again, remember, aqueous solutions, solids, liquids would be dropped out of the equation. So if I'm looking at substance A, so when we are looking at converting from Kc to Kp, we're going to use the conversion to get my pressure constant from my concentration constant. So I'm going to take my concentration constant at equilibrium and multiply that by RT. R, again, is my ideal gas law constant you would be given. T is the temperature in Kelvin at which it's happening. And we're going to raise it to the power of the change in the number of moles. The moles of gaseous product minus the moles of gaseous reactant. Product minus reactant. Let's try one. So this says, in the synthesis of ammonia from its constituent elements. So we need to write this equation. Ammonia is NH3. And ammonia is a gas, here we go. So its constituent elements. Its elements would be nitrogen and hydrogen. So nitrogen, when it's by itself, is diatomic, so it's N2, gaseous state, plus hydrogen, again, by itself is H2 in the gaseous state, and it's going to be at dynamic equilibrium. And we need to balance this equation here. So I've got 3 hydrogens, so I'm going to have 6, so that would be 3, and that would be a 2. We should be balanced. And it tells us that Kc is 9.6 at 300 degrees Celsius. So before we even get going too far, let's change Celsius to Kelvin because we're going to need to. So 300 degrees Celsius plus 273 is 573 Kelvin. All right, calculate the Kp for this reaction at this temperature. So remember we said that Kp, just from the slide before, Kp was equal to Kc times RT raised to the change in the number of moles. So let's look at this. Delta N is gaseous products minus reactants. Okay, so let's look at how many products of gaseous molecules do we have? How many moles of that? I have 2. And I'm going to subtract how many moles of gaseous reactants do I have? I'm going to look and I'm going to say, well, I have 3 there. And I have how many here? There's a 1 there. It's implied that it's 1. So I'm just looking at this one and this one. Again, all of the stoichiometric ratios. So my reactants, I have 3 plus 1, I have 4 reactants. So 2 minus 4 gives me a delta N of -2. All right, so now it's just plugging in what we know. Kp, so the pressure constant, Kp, for this reaction at this temperature, I would plug in my Kc, 9.6. Again, there's no units attached to it. And then I'm going to put in my 0.0821 because that's liters, atm, Kelvin, mole, times 573 Kelvin, and that's all raised to a power of -2. So let's plug that into our calculator real quick. So when I multiplied 0.0821 times 573, I got 47.0433. I'm going to raise that to the -2. And after I do that, I need to multiply it by 9.6 still. So let's raise this to the -2. And then I'm going to then multiply by 9.6 to get an equilibrium pressure constant of 0.00, how many sig figs? 3 sig figs? 0.00434. And we can see that these are significantly different numbers. My equilibrium constant for pressure, 0.00434, compared to the equilibrium constant as far as concentration at 9.6. So we can see that those numbers are very different. Should we try one more? Let's do it. So for the equilibrium of sulfur trioxide gas decomposing, so let's write sulfur trioxide, so SO3, and that's in the gaseous state. It's decomposing in its equilibrium, so let's write it like this. Decomposing into sulfur dioxide gas, so SO2 gas, and oxygen gas. O2, remember, is diatomic. The Kc is, let's write our Kc, is 4.08 times 10 to the -3. And we're at 1000 Kelvin. Calculate the value for Kp. So let's first balance this equation. I've got 4 O's on the left, so I need, let's try to get to 6 O's. So let's put a 2 here, then I would need a 2, so that would give me 4 O's, 5, 6 O's. We should be balanced. That would just mean I'm just going to write a 1 there just for kicks. You don't need to, that's implied. So again, we've got our equation that says that Kp is equal to Kc times RT raised to the change in number of moles. So let's find the number of moles. We're going to take our gaseous products. So our delta N is equal to how many gaseous products do we have? 2 plus 1 is 3. I'm going to subtract my gaseous reactants, and here's my gas reactant. I've got 2, so 3 minus 2, so delta N is 1. All right, so now we're just going to plug in, so Kp is equal to 4.08 times 10 to the -3 again, is just a number. I'm just going to put that in parentheses so we don't get stressed out by it. And our R, 0.0821 liters, atmospheres per mole Kelvin. Well, I'm just going to do mole K, MOL, mole Kelvin, times temperature, 1000 K, all raised to the power of 1. So I'm going to take my calculator and I'm going to do 0.0821 times 1000. And if you feel inclined, we're going to throw that to the power of 1, which should give us the same answer, 82.1. And then we're going to times it by 4.08 times 10 to the negative third times 4.08 times 10 to the negative third. And we would get a Kp value of 0.3. Let's see, how many significant figures? 3.335. And again, we can see that difference between 0.335 and 4.8 times 10 to the negative 3 would be 0.00408. So hopefully you're feeling good about that conversion. So what are these equilibrium constants telling us? And I keep saying we've been looking at the magnitude of that number. Well, we can have very large numbers, we can have very small numbers. If K is large, then the equilibrium lies to the right. The product is favored to the right. Or I mean, the products are favored and the reaction is favored going to the right, which is to the products. Because remember that K is equal to products over reactants. And by doing this division problem, how would you get a bigger number? Well, you would need a larger number on top, right? If I only did 1 divided by 2 as opposed to 10 divided by 2, I'm just using easy numbers here. 1 divided by 2 is 1/2. It's a small number compared to 10 divided by 2 of 5. So if I have a larger number on top or greater concentration of products, so if K is large, then we have product favored reaction. Now, if K is small, then we have a reactant favored. So the equilibrium lies to the left. The reactants are on the left. Now, if K is equal to 1, how would I get, if I'm dividing two numbers, how would I get 1? Well, we would need very close to the same number on top and on bottom. So we would have about equal number of products and reactants. So again, this number, this constant, is really interesting to a chemist because if I have a large constant, then we know that my products are favored and it lies, that equilibrium, remember where our concentrations are equal, lies far to the right. If the reactants are favored and I have a small constant, then the equilibrium lies to the left. And again, if it's close to 1, it's really close to being right in the middle, being equal. So what if we were to write the reaction reverse? How would I write K? So what we've done so far, if I had this pretend equation where I had AA plus BB reacts to form so many moles of C and so many moles of D. To find Kc, we did products over reactants. So I did C, concentration of C to the C, concentration of D to the D over my reactants. So I've got my products over reactants. So my reactants A, B, A, B. Now, what if I wrote this in reverse, right? Let's say I reverse this reaction. So now for my reactants, I have C plus D reacting to form A plus B. Well, my Kc is just going to be opposite. My products are now my A and B. And my reactants are now C and D. So it's just the reciprocal to what Kc was before. So the reverse reaction, if I first initially had Kc, then my reverse reaction is just going to be Kc prime, or the reciprocal to what we had originally found. So let's look at this example just before this, or a couple examples ago. We looked at the formation of ammonia from its elements. So we had N2 and hydrogen gas creating NH3. Now, two of them. Now, what if we flipped this reaction? We're told that the Kp value is 4.34 times 10 to the negative third. Now, if I just flip this reaction, so let's say that I started with 2 NH3, and it's going to decompose into N2 plus 3 H2s. What happens to this Kp? All we need to do is find that Kp prime, or the reverse, which is 1, or the reciprocal, 1 over Kp. So I'm just going to take this Kp, this 4.34 times 10 to the negative third, find out what 1 over that is. So let's just get our calculator. So if I take that reciprocal and I plug it into my calculator, 1 divided by 4.34 times 10 to the negative 3, I get 230.4. So Kp prime, we'll call that. Now, if you think back to when we were just talking about interpreting what those constants mean, we said if I had a very large K constant, that the equilibrium lied to the right, to the products. So I would say that 230 is pretty large compared to 4.34 times 10 to the negative 3, which would be 0.00434. So again, a very large K constant says that our equilibrium lies to the products. So this is telling me that my products are favored with this very large value. Now this is the same equation as that, it's just the opposite, right? We just flipped it. So in this reaction, N2 plus 3H2, this is where my reaction, to get to equilibrium, it's far right towards my products. Now, we also said a very small K constant, the equilibrium lies to the left. So in this equation, interesting how it's going to the product favored. So equilibrium is on the left, or closer to my products. And if you notice, it's the same species that it's leaning towards. Now, if we multiply the equation by a constant, similar to what we would do in Hess's law, then the equilibrium constant, we're going to figure out what that would look like. So if I took my equation that I was using before, we have reactants A and B in dynamic equilibrium with C and D. But let's say that I multiplied everything by 2. So whatever my coefficient was, I times it by 2. I put a 2 in front of everything. Now, that changes my K constant. If I multiplied, so everything was multiplied by 2. So when I'm finding my K constant, I would have my products over my reactants. So I would have C to the C power times 2. That changes that exponent, or that power, times D times 2. So that's my products over my reactants. So this would change that equilibrium constant just because my power would be all raised to the second power. So let's look at this and give it some thought. How does the magnitude of the equilibrium constant, Kp, for the reaction? So if I have 2Hi in dynamic equilibrium with my hydrogen and iodine, how does it change if the equilibrium is written as 6Hi in dynamic equilibrium with 3 H2s plus 3 I2s. So we can see that the same reaction is happening here with hydrogen iodide breaking down into its constituents of hydrogen and iodine. But here we can see going from 2 to 6 that we just multiplied or we distributed a 3. Right? Or we multiplied by 3 to get from 2 to 6, from 1 to 3, 1 to 3. Okay, so we compute what our original K constant, or our Kp, our pressure constant. So we're going to look at our products over our reactant. So we would take the partial pressure of hydrogen, and notice that it's only to the power of 1, times it by iodine's partial pressure again. Oh, shoot. Partial pressure of iodine. Goodness, I'm just going to scratch that. There we go, scratch that up. So there's my products over my reactants. So I would have the partial pressure of Hi. That is to the second power. So this is my initial. Now let's look at my Kp for the new equation. All right, so we're going to do my products over reactants. So I've got my partial pressure of H2 cubed. Then I have my partial pressure of iodine cubed over the partial pressure of Hi to the sixth power. So my original K, what's essentially happening for going from my original to my new, I am cubing it. So I'm not just timesing it by 3. So this kind of helps us to see, yes, I'm timesing it by 3, but look at the difference when we write the initial and the final. I went from a power of 1 to a power of 3. Went from power of 2 to a power of 6. What about when we're looking at Hess's law and K values? So when we are, let's say we're looking at 2 NOBRs in dynamic equilibrium. So 2 NOBRs decomposing into 2 NOs plus diatomic bromine. And then we have bromine, diatomic bromine plus diatomic chlorine in dynamic equilibrium with chromium chloride. And we're given the Kc constants for both. What's the value of Kc for the net sum of the equations above? So if I'm looking at my net equation, so here's my 2 elementary equation 1, elementary equation 2. This is my net equation. So if we look at this, and again, I'm going to fix these here. So I've got Br2 and Br2 on opposite sides of my arrows. So we're just going to cancel them out. And notice that I have 2 NOBR and I have 2 NOBRs. So we're going to leave that be. All right, we're good here, good there. I also have on the left side of my arrow my Cl2, we're good there. 2 NOs, and 2 bromium chlorides, 2 bromium chlorides. So there is my net equation. We're good. So how do I find the value of Kc? Well, if I look at Kc, if I looked at my products over reactants. Now let's take a second here, and if I looked at all of my products, before I canceled out, using Hess's law, before I canceled out this product of bromine, let's just look at if I did my NO squared, bromine, There's no, there's only 1 in front of it, right? And let's say I did BRCl, and that's also squared because I have 2. So product over all of my reactants. I'm going to write all of these down. NOBr squared, 1 bromine, 1 chlorine, diatomic chlorine. So here we can see cancel, cancel. So yes, now when I look at my products, I have my NO, my BRCl, again, squared, square, and my reactants, NOBr squared, chlorine, diatomic. So these are both canceled out. Now, when I am looking for the net constant, it's a little different from when we use Hess's law with finding delta H. When we're finding the net constant, we multiply the KCs. So we're just going to take 0.014 times 7.2. And when I do that math, 0.014 times 7.2, I should get 0.1008. So the net sum of the equation with the value of Kc will be 0.1008. So a few points that we just were talking about from this last couple slides. If we take the reverse direction of an equation, we take the reciprocal of the original K. So it's just 1 over what that original equation was when we flip-flop the direction of the equation. Number 2, important takeaway. If you add a number through the equation, you need to raise that K constant to that power. So that example before, when we multiplied 3 throughout it, we then had to take our K and raise it to the power of 3. And thirdly, if we add equations together using Hess's law, we multiply the K values. And again, that's a little different than what we did with Hess's law and delta H. We need to, when we are finding that K constant values and we're trying to find a net equation from those elementary equations, then we multiply the K values. Those are really the big 3 manipulations that you just need to be aware of when you are working through finding K constants with different equations. All right, so let's look at an example. Let's say that I have HF in dynamic equilibrium with hydrogen ion and fluorine ion. We're given a Kc value. And here I've got H2C2O4 in dynamic equilibrium with 2 H's and C2O4's -2 value. We're given Kc's for both. Here's our 2 elementary reactions. And I want to determine the value of Kc for the reaction of 2HF. All right, so I'm just starting with what I'm given here first. Well, I like that HF is on the left side of the equilibrium sign, on the left side of the arrow. Up here, HF is on the left side of the arrow, but I only have 1. So I need to multiply everything here by 2. All right, that will give me, if I rewrite this equation, 2HF in dynamic equilibrium with 2H plus 2F minus. And that means I'm going to take my Kc value of 6.8 times 10 to the -4th, and I need to square it, right? Because I distributed 2 throughout it, so I need to square my Kc. All right, then let's look and see. Okay, so I've got that taken care of on the left. C2O4. Let's see, where's C2O4? It's right here, but it's on the right. So what I need to do is flip this equation. All right, so I'm going to write C2O4 plus 2H plus in dynamic equilibrium with H2C2O4. Okay, so because I flipped my Kc value, I need to take my Kc value here and take the reciprocal of it. 1 over 3.8 times 10 to the negative 6. All right, and let's just double check here and make sure that we have our net equation. Let's just double check. So I've got 2HF on the left, plus C2O4 in dynamic equilibrium with 2F minus, there's 2F minus, plus H2C2O4, there we go. And then I've got 2H pluses on the left that are going to cancel out with my 2H pluses on the right. Okay, so then I just need to multiply my two K constants, right? So I've got 6.8 times 10 to the negative 4th squared times 1 over 3.8 times 10 to the negative 6th. And let's just do our math here. And when I squared my 6.8 times 10 to the negative 4 squared, I got 4.6 times, or 4.624 times 10 to the negative 7th. 1 over 3.8 times 10 to the negative 6. I got this very large number. And when I multiplied the two together, I got 0.12 with sig fig values. I'm going to 2 sig figs because that's what my Kc up here is, 2 and 2. So I'm going to say my Kc value for this net equation is 0.12. Good work on that last one. Okay, let's try another one. Okay, so here we are, give it at 700 Kelvin. We've got a pressure constant of 54.0 for the reaction of hydrogen gas and iodine gas combining to form hydrogen iodide gas. So let's write this. Hydrogen gas is H2 plus I2 in dynamic equilibrium to form 2 HIs. I had to balance that, right? Because these are diatomic in their original state. 2HI and our Kp is 54.0. Okay, also a Kp, so we've got a second one. Kp is 1.4 times 10 to the negative 4th for the reaction of hydrogen gas and nitrogen gas combining to form ammonia. Oh, we did that one already. Hydrogen gas plus nitrogen gas combining to form NH3. We did this, 2 and 3. There we go. So we've got that. Now, determine the Kp for this reaction. Gaseous ammonia. So we need to figure out, I'm going to do this, and let's figure out, we want gaseous ammonia, NH3, reacting with iodine gas to form gaseous hydrogen iodide and nitrogen gas. Okay, let's balance this reaction. All right, there we go, balanced. Now, we need to figure out how to get to this target equation. So if I have, let's start with our first one, NH3. Well, right now the NH3 is on the right of this equation, so we need to flip. And remember, if we're going to flip, that means we need to do what? Take the reciprocal. So this is going to be 1 over, so down here I'm going to do 1 over 1.4 times 10 to the negative 4th. So let's flip this equation. We're going to do 2NH3 produces 3 H2s plus N2. All right, and then, so that gives us our 2 NH3s. We need 3 I2s on the left. But right now we have 1 I2 on the left, so we need to times all of these by 3. 3 times 2 would be 6. Okay, so let's write that. I would have 3H2 plus 3I2 would produce 6HI. So we need to, if we're distributing by 3, remember we're going to take our Kp, we're going to put it to the third power. Let's just make sure we get what we need here. On the left, I've got 2 NH3s and 3 I2s. On the right, I have 6 HI and N2. And then look, my 3 H2s cancel out. Perfect. So now we just need to multiply our Kp's. So I'm going to slide this up here. I flipped this reaction, which means I take the inverse of that Kp. So I've got 1 over 1.4 times 10 to the 4th. Now I'm going to multiply it by 54 cubed because I had to distribute my 3 throughout that whole equation. So when we do that math, I do 54 cubed, 54 to the third power. I'm going to times it by, in parentheses, 1 divided by 1.4 times 10 to the negative 4th. Ooh, we get a very large number. We get 1,1,2,4,7,4,2,8,5,7. Holy smokes. This is really large. Oh, I can't write while I'm talking. So this is really, products are definitely being favored. And we would want to write this into scientific notation using 2 significant figures. So what would that be? 1.1 times 10 to the 369th power. So far, we've had homogeneous equilibrium. So we've dealt with reactions and products where all were in the same phase, whether they were aqueous or in gaseous phases. But we can use K in terms of either concentration or pressure if they're different. So far, they've been all in the same phase. So looking at heterogeneous equilibria, if the substance and equilibrium are in different phases, like here we have solid lead chloride in dynamic equilibrium with aqueous lead ions, lead plus 2 ions, and chloride ions that are in aqueous solutions. So you might think, okay, well, we would do products over reactants, but how do we express the concentration? Because concentration, if you think, and you remember back to concentration, Kc, concentration is measured by molarity, which is how many moles per liter there are with the substance. And that doesn't apply to solids or liquid. I mean, it's only for aqueous and for gas phases of matter. So this is only applicable, only phases of matter that we can find Kc for, only phases of matter for aqueous solutions or gaseous solutions. So you think, well, how do we express it? We don't. You leave it out. So in this case, if I were to look at products over reactants, I would do, okay, my products are, for Kc, the concentration of Pb plus 2 ions, and there's no exponent there. And then we have our chloride, Cl ions, raised to the second, products over nothing. This would be my concentration constant for this equation. We never include, let me even write this, never include pure solids or pure liquids in the expression Kc for concentration. And if you think about pressure, it's right up here. Pressure is only gases. Only gaseous substances are applicable to Kp for pressure. We measure pressure in atmospheres, kilopascals, but that's only for gaseous substances. So if we were to look at this expression here, evaporation of water in terms of partial pressures. So if I looked at water, H2O, water in liquid form, as it evaporates, so it's in equilibrium, dynamic equilibrium with H2O in the gaseous phase. If I looked at my equilibrium constant for pressure, we would look at products over reactants. But in this case, I would only have my partial pressure of H2O because I would do products over reactants. But here we do not include the liquids. So my pressure constant would simply just be the pressure of H2O that's in the gaseous stage. That's it. And this is showing us evaporation. So all we do is we're excluding any solids and liquids from the equilibrium constant expression. I would just have this be the products over reactants. It would just be my product, my gas, over 1 or nothing. Okay, so let's try writing the Kc and the Kp for the decomposition of calcium carbonate. So calcium carbonate, CaCO3, is a solid, and it decomposes into calcium oxide, which is a solid, and CO2 bubbles, which is a gas. So if we looked at my concentration, Kc, I'm going to do products over reactants. Again, for my concentration, I'm only looking at gases and liquids. The only product that's a gas or liquid is CO2. So I would just do my concentration of CO2, and it's a balanced equation, so just to the power of 1. Products over reactants. There's no reactants that are gaseous or liquids, so that's it. That is all I would do for Kc. Let's look at the partial pressure constant. This is only gases. So in this case, I would look, okay, products over reactants. I would look at the partial pressure of CO2, again, to the first power. And I have no reactants in gas, so again, that's it for my constant pressure. So solids and liquids drop out of Kp expressions. Solids drop out of Kc calculations. It doesn't make any sense to measure the concentration of a solid, right? We know solids, or we know that gases and liquids, we can calculate how many moles per liter are there, right? That's the concentration. As far as pressure, gases are the only thing that's exerting pressure, so we're just looking at gas species.